Good evening to one and all. Today's concept is about the continuation topic about the data flow analysis. And here I'm going to explain the remaining two properties of data flow analysis in global optimization. And in the last classes, I explained about the two properties. What are those means? Available expression is one of the property for the data flow analysis, and the next one is about the liveness variables, and that we are also calling it as an liveness analysis. And I explained these two properties in the last class, and today class I am going to explain about the next property of data flow analysis, that is about very busy expressions, or we can also call it as a just it is a busy expression, right? And here, what is a busy expression? When we say that it is a busy expression, an expression is very busy at a point P when if and only if on every path from P, that is E, the expression is evaluated before the value of E is changed. Then we can say that it is a busy expression. And here again, I'm giving another definition of how to define the busy expression means. An expression is said to be a busy expression along some path, some Pi to Pj, if and only if an evaluation of the expression E exists along some path Pi to Pj and no definition of any operand exists before its evaluation along the path, then it can be called as an busy expression. And here how the optimization takes place, and after performing the optimization and what type of an output that we are expecting here is, and it can this type of an property can host very busy expressions computation. And here we're having a problem. What the problem is, it may be in forward or backward problem, and it is always a backward problem. And here we're having it may be in may or must. Always the busy expression should be must. The liveliness is in may, and the expressions, available expressions are must. And again, the busy expressions are also comes under the must, right? What this must means, just see here. See in the previous slide, what the must and what the may is. Here we're having, see, these are the two forward, and must comes under the available expression. And while coming to the liveliness, when we are talking about the liveliness, and here for the liveliness, we are having may. We are having may. See, and see here we are using may. Liveliness is also a backward may problem, and these expressions are forward must problem. And while coming to the today concept, that is about the busy expressions, it is backward must problem. What kind of problem it is? It is backward must problem. While coming to the available expressions, it is forward must problem. And liveliness analysis, it is backward may problem. I think you understand what kind of problem it is means. It is backward must problem. And here, when we can say it is an busy expression means if and only if the condition satisfied like this, then only we can say that it is a busy expression. What the condition is here, on every path from P, the expression is evaluated before the value is changed. Make a note of this. Before the value is changed, then we can say that it is a busy expression. And now, and after performing the optimization techniques, then for the property like an busy expression, what type of an output that we are expecting here is, we can host very busy expressions computations. So performing the optimizations, we can host very busy expressions computations, right? And what is code hosting? What is code hosting? And here what the advantages of busy expressions means, busy expressions are useful in performing code movement optimization. This code movement optimization is also one type of a transformation in principal sources of optimization. Once recall that. This is another transformation technique in principal sources of optimization. That's where this is an advantage here. These busy expressions are useful in performing code moment optimization, and the available expressions are useful in common sub-expression elimination, right? And the liveness variables are useful in dead code elimination. While coming to busy expressions, and here what the advantage is, they're useful in performing the code movements or code motion. We can call them as an code motion. And here, by performing the data flow analysis, we get available expressions, reaching definitions, live variables, and busy variables. And these are all are useful for applying various global optimizing transformations. What and what those means, such as global common. Here, where I am making note here, I am calling the common sub-expression elimination with global, because we are having two types of operations, right? Whether it may be a local operation or global operation. So, and where the optimization transformations can be applied in a global means global common sub-expression elimination, copy propagation at code movement optimizations, and at the elimination of induction variables. And these are the some of the transformations that we are going to apply this global optimizing transformations, right? And what the next concept is about in code hosting. Code hosting. What do you mean by code hosting? What do you mean by code hosting? See here. See, what is an code hosting? Code hosting finds the expression. That means that are always evaluated following some point in a program. And here, regardless of the execution path, and moves them to the latest point beyond which they would always be evaluated. And that we are call it as an code hosting. What the role of the code hosting is, it always finds the expressions. And what type of an expressions it is going to be find out means the evaluations, finding out the evaluations based on what, based on some point in a, but following some point in a program. And here, and regardless of the execution path, and moves to the latest point beyond which they would always be evaluated, then we can say that it is an code hosting. And it is a transformation where that almost always reduces the space occupied. When you want to reduce the space, then we need to apply this transformation. What the name of the transformation is? The name of the transformation is an code hosting. Code hosting. And always reduces the space occupied, but that may affect its execution time positively or not at all sometimes. So this is an advantage here. This is an advantage here. To reduce the space occupied, that means reducing the space, we need to apply the transformation like in code hosting, right? But it should not affect any type of an execution. It may be time positively or may not be. Make a note of this. This is the most important transformation technique, because to get our target code in an efficient manner, this transformation plays a major role just by reducing the space, right? And what the next property is, reaching definitions. Reaching definitions is another property for data flow analysis. This is the most important property here. What the meaning of this reaching definition means? Here, a definition within D, and defining a definition within D. When a definition D reaches at point P, if there is a path from D to P, if there is a path from D to P along with D is not killed, along with D is not killed. And here we are also using the definition use information, and what we are going to define and what we are going to use, and what the definition of this reaching definition means. A variable v is an assignment to v, right? So a definition of variable v reaches to some point p, when if there is no intervening assignment to v, then only it can be called it as a reaching definition. And here what kind of problem it is means, it is forward may problem. Forward may problem. And this is also and one of the most important property for the data flow analysis. And these are all the properties of data flow analysis of the flow graphs. And up to now I explained the available expressions, liveness analysis, busy expressions, and the next property is about the reaching definition. These are the four most important properties under the data flow analysis, right? And here the space of data flow analysis is because what kind of problem is some at one property I'm calling it may be in forward must, or it may be in forward may, or backward must or backward may. And see here we're having the four important properties here: reaching definition, available expression, live variables, and very busy expressions, right? So these two, reaching definition and available expressions, are forward, it comes under for, it is forward may problem and it is forward must problem. It is backward live variable, live variables are the backward may problem, and it is very busy expressions are the backward must problem. Is it clear now? And this shows the space of the data flow analysis, space of the data flow analysis. And here we're having an advantage of reaching definition is at in every property I give the example, and while coming to the property like and reaching definition, here what the advantage is, these are used in constant and variable propagations. Constant and variable propagations, where these are the two, this is the transformation again from the principal sources of optimization, right? And here the most data flow analysis can be classified in this way. If you don't fit, that means here we're applying the bidirectional, and lots of literature on data analysis we're doing here. And up to now I explained about this data flow analysis, and here I'm giving what the properties of the data flow is, what the most important properties of the data flow, because I completed the topic of the data flow properties. And now I am giving the property data flow properties. That means I explain what and what the properties are here. And before discuss, actually this thing I need to discuss before the starting of the data flow properties. But now again I'm explaining this. I'm discussing with you this data flow properties should consider some basic terminologies that will be used while giving the data flow property. What are those terminologies means? A program point containing the definition, whatever the program point, a program point containing the definition, then it can be called it as a definition point. A program point at which a reference to a data item is made, then it can be called it as a reference point. And a program point at which some evaluating expressions is given, that can be called it as an evaluation point. I think that here we're having three points. One is definition point, another one is a reference point, and the next one is an evaluation point. And when we can say that it is a definition point means, here we're talking about a program, right? So a program point, if the program point contains the definition, then we can say that it is a definition point. And if a program point, when we are referring to any type of a data item, then we can say that it is a reference point. And here I'm performing some evaluation for the expressions in a program point. Then I can say that it is an evaluation point, right? These are the three most important terminologies when we are discussing about the data flow properties. These are the three most important terminologies that we are going to use when we're defining the properties. But that means when we are knowing what the context of each and every property means, there we are having these terminologies. What the meaning of these terminologies means, just I explain now, right? And here these are all not under our syllabus. As per our syllabus, these are all not, we are not having, these are all topics. And here we are not talking about what the lattices and what the partial orders or the continuation of the lattices and useful lattices. And up to this concept we are having, that means only about in the global optimization, only about knowing about what the data flow analysis is and what the control flow analysis is, and how to represent the control flow graphs, and how to operate the data flow analysis on the control. That means the data flow analysis are operates on the control flow graphs, right? And with the properties of these four, these data flow analysis operates on control flow graphs. And with this, as per our syllabus, the code optimization concept was completed, because in the last classes I explained about, I start with what the basic transformation techniques are, what the basic transformations are. That means with the concept of the principal sources of optimization, I explained what the transformations that we are having in principal sources of optimization, and then what is a loop optimization, and what the transformations under the loop optimization, and what is a peephole optimization, and what are the transformations under peephole optimization, and then I explain about the local optimization. And after local optimization, in last in today's class, I explained about the global optimization. And when we are performing the global optimization, totally we need to use the data flow analysis. By using the data flow analysis, we can apply all the global optimization techniques. Make a note of this. And whatever the optimization techniques that we are performing under the global optimization means, it, it should be an global. Any transformation should be an global. And if any transformation that we are applying from the local optimization is by using the local optimizations, or when we are performing the local optimizations, there itself you want to perform any type of a transformations means, then it can be called it as a local transformation, right? And a simple difference between what the local and what the global is, just only performing at certain specific blocks, then we can say that it is a local optimization. And throughout the program or within the procedures, when we apply the optimization techniques means, then it can be called as a global. That's why it is a broad scope, where we are naming it as it is a broad scope. And while coming to the local, it is a limited scope. It is having a limited scope, and the global optimization is having a broad scope. Is it clear? And these are the most important the differences between the local and the global. And in the local optimization, totally we are knowing about what the basic blocks and what the loops in flow graphs and how to draw the flow graphs, and what the terminologies that are under the loops in the flow graphs. We learned all those things. And when coming to the global analysis, in the that is in global optimization, only we are concentrating on data flow analysis, because by using the data flow analysis only we can apply the optimization like a global optimization. This global optimization is performed by using the data flow analysis. And from where we are applying this data flow analysis means, just we are operating on the control flow graphs. That means there is a connectivity between the optimization to optimization. If you know what the basic block, if you know what the flow graph, and if you know how to represent the control flow graphs and all those, then only you can understand how to apply these properties of the data flow analysis on the control flow graphs, right? And this is the most important concept, the global optimization and the local optimizations in code optimization. And with this concept, the total code optimization phase was completed. And now we are entering into the next phase, that is in code generation. And what the output that we generated here, the output, it is an optimized code. The output is an optimized code. That is, it is an optimized intermediate language. That means there we improve something. We are showing that we improve something. How we are showing means, not by taking the variables or not by seeing the expressions, just made by seeing the lines of the code, just by checking at the lines of the code, and what the code we generated at the intermediate phase and what the code we're generating at the code optimization phase. Just by comparing these two, then we can easily understand, it may be reducing of the lines of the code, or it may be reducing the space of the code, whatever it may be. Totally our target is to improve the efficiency of the code, right? So to improve the efficiency of the code, what the transformation that we need to perform to optimize the code by by using this code optimization. That means by implementing this code optimization, we are implementing all those. We are performing all those, right? So finally, what the code I get here? It is an optimized intermediate language code, because The code consisting of some translation statements. It is in the form of a three address code representation. That's why I am naming it as an optimized intermediate language, because once recall what the output that we get at the syntax analysis, there we generated the parsers, right? Parse trees. And what the output we generate, we get at the semantic analysis, the same output, nothing difference is there, the same structure we are showing here. But with the tools like in type checker tools, what we're doing here is we're checking the structure, we're checking the representation. That means we're checking the parsers just by using some tools, by implementing some automaton tools. And what we done there, just decorate we get an decorated abstract, or it may be a parse tree or abstract syntax tree, whatever it may be, the tree we're generating in the both phases, right? And here also, after this code optimization, what the output you generated means the same output in the form of an intermediate language, but it is an intermediate language optimized intermediate language code. Is it clear now? And now I want to give this optimized intermediate language output as an input to the code generation. And next, what the next phase it is? The next phase is an code generation. And by using some algorithms, totally now I am entering into the machine dependent code. Up to now, I am some in machine dependent and some part in and machine independent. Because I'm totally not, this code optimizations and the intermediate languages are totally not an independent codes, machine independent codes. Somewhere we're depending on the machine level instructions and somewhere we're not depending on the machine level instructions. So, and up to this phase we're talking about a machine independent code only, and now we're totally entering into the machine dependent code. Right. That means the final generated code is should be in the form of an machine level language. It should consisting of all the assembly, all the arithmetic logic units, all the registers, all the instruction sets, and mixing of some intermediate registers, and so on and so on. So, and from the starting of this code generation, I'm going to discuss about how the conceptual view looks like. That means I will explain about the role of the code generation, then entering into knowing about some algorithms, and with the algorithms and how the implementation takes place and how we're generating the final target code. And with that code generation, totally the process of compilation with all the 6 phases was completed. So, and then after completing the code generation, finally we are generating the target code, right? That is in the form of the object code form. Then by giving an input, totally performing the process of compilation with all the 6 phases, finally we generate the output. And uh, after knowing the code generation, then we can clearly understand what the internal functionalities are, what the internal functionalities of each and every phase is, and how they implemented with those internal functionalities, and what the techniques that we used and the tools that we used there, and all those we already understand, because at each and every unit we are learning about a single phase. That means in lexical analysis I explained about the lexical analyzer, and in syntax analysis I explained about, that means in unit 1 I taught the phase 1. In unit 2, I thought about the phase 2. And unit 3, I thought about the both phase 3, and that means the syntax and semantic is merged in unit 3. So in the unit 3 also, I thought about a semantic. And in unit 4, I thought about the fourth phase. And this is in the 6th unit as per our syllabus, and where it is the half of the code optimization concepts. So in unit 6, the half of the syllabus is covered with the fifth phase. And in unit 6, the remaining half of the phase should be covered with the sixth phase, that is code generation. Finally, totally the all 6 phases are completed, and we generate our target code, which is an efficient code. And then after completion of this code generation, I am going to explain about the symbol table, right? And after knowing what the symbol table is, and what the concepts under the symbol table, and how the runtime environment takes place in symbol table, and how the storage allocation takes place in symbol tables. By explaining all those, totally our syllabus, all the 6 units are covered. And the subphase of the symbol table also I explained in the unit. I will explain in the unit number 5. And the remaining another subphase is it is about the error handler, right? So this at each and every phase itself I am talking about the error handlers. Why? Because we are having some commonly occurred errors, right? So there itself I am talking about if we are implementing the lexical analyzers, what type of commonly occurred errors to be encountered. If we are talking about the syntax, what are the commonly occurred errors that are to be encountered. If you encounter the error means you should handle that and you should modify and you should update and you should generate an error-free output, right? So this is the overall process of compilation that we are relating with as per our syllabus. Is it clear? From today's class, in today's session, the concept of code optimization was completed. That means I completed the 5th phase. And in the next class, I'm going to discuss about the next phase of the compilation, process of compilation, that is the last phase, the 6th phase, code generation, right? And here we're having some data flow equations like that. But if you know what the equation in this in code optimization at the local optimization and global optimization, we're having in the last class I explained about the properties, right? The two properties. And today class also I explained about the two properties. And when I'm explaining about the two properties, we're having some data flow equations as a concept. And what those equations are, those equations are the equations that representing the expressions. That means that are appearing the flow graph. And by using these equations, uh, we can compute the live variables and available expressions and reaching definitions. That means if you know what the equation is, we are not going an internal implementation just by performing all these computations by using these equations. We are not doing all those. Just we are knowing what the equation is. If we are having an in statement, what type of an equation that we need to use and how to compute that. And if you are having an out statement, if we are having a generation statement, if we are having a kill statement. And for this, we are having the equations, right? We are calling them as a data flow equations. And these equations are only representing the expressions and that are appearing in the flow graph. And when we are using these equations means these are all useful for performing the data flow properties, performing the computations of all these data flow properties. That means first of all we have to understand how to represent the data flow equation. If you understand the representation, then as per our syllabus that is enough. No need to go and in detail of learning the computations just by solving it, right? And in the last class I show you the equations of the in statement, out statement, generation statement. Gen is nothing but a generation statement, kill statement. And with this data flow equations we can construct the programming. These equations are useful for constructing the programs. This much information is enough for you all as per our syllabus. No need to go in detail. If you're having if you will see any type of computations by using these equations means as per our syllabus there is no need of learning all those. Just knowing the representations it is enough. And no need to go and in detail learning of the data flow analysis. Up to global optimization, if you know what the global optimization is and what the two types of representations in global optimization. One is in control flow analysis and the one is in data flow analysis. And knowing about what the control flow analysis is and knowing about what the data flow analysis is and what the transformations that we are applying in the data flow analysis at code at the global optimization. And up to this it is enough, right? And no need to learn, no need to go in detail about the computations, performing the computations. I think you all understand the code optimization phase. If you have any doubts, you can please ask. Any doubts? Anyone? I think no one is having any doubts. And the today's session is completed just by knowing about the remaining two topics of the data flow properties and knowing how the space of this space of data flow analysis can be represented in a table representation like this, and knowing what the liveness and what the reachable definitions and what the busy expressions and what the available expressions and all those. And then I'm concluding the today's session with these concepts. And in the next class, I will start with the last phase of the process of compilation, that is about code generation.